So in this video we will study about the weak bases, and weak bases there are major two types are there. Number one, it is called conjugate base of the weak acid or amine bases. For an example, acetate ion, cyanide ion, chlorate ion. And amine base are ammonia derivative, methylamine, and then these are like ammonium ion, C6H5, and so what happen if you see that here we have ammonia, NH, H and H. This is ammonia, and if we replace one proton from ammonia with some kind of CS3 group, so this become amine. So this is methylamine, and if we replace two hydrogen with methyl group, this is called dimethylamine, and if we replace third one, then it will be NN-methylamine. This is methyl NN trimethylamine, CS3 and CS3. So this is primary amine, this is secondary amine, and this is tertiary amine. And if we have one more amine, it will become quaternary salt, for an example. And all the amines, when they react with the water, basically what happen here, you can see this lone pair of electron in the nitrogen, it accepts one proton from the water. So proton act as an acid, and then ammonia behave, or amine behave like a base proton acceptor, and it increases the hydroxyl ion concentration in the water. That is why they increases the pH when they dissolve. And the table 16.4 and the appendix D contain list of the weak bases and their Kb. So what is the Kb? As we have seen in the previous slide, that when we write, let me use this slide first. So weak base we can represent must be included in the water. Weak base reaction must be in the water, and once they react with the water, basically you can see this is showing a heterogeneous reaction where water act as a liquid or solvent which do not take part in the equilibrium writing. And when we write the equilibrium expression for this weak base, basically we write Kb. So Ka for acid, and Kb for base, right? So Kb for base is exactly same as product over reactants, as we were writing about the Kc or Kp or Ka or even Kw. So B subscript shows that we are discussing about the base or dissociation constant for the base, and this will be like a Hb ion one product, hydroxyl ion another product, divided by reactant base. We do not include the water because it is a solvent and or pure liquid which is not take part in the expression. Let's talk about the Kb in little bit more. That if you see, there are different types of weak amines, and mostly they are nitrogen base, ammonia derivative, this is ammonia NH3, this is pyridine C5H5N, and hydroxylamine. In this one, what happened, basically one proton once you will replace with the hydroxylamine, this is called hydroxylamine. If you will replace one hydrogen of ammonia with the methyl group, it will call methylamine. And hydrosulfide ion, carbonate ion, and hypochlorite ion. So these are all behave as a weak base in water at 25 degrees Celsius. So these values for the Kb values, they are measured values at 25 degrees Celsius, and their conjugate acids. Conjugate acid means once they accept one protons plus one proton, right? Once they accept, they are called conjugate acid. So this will be ammonium ion, pyridinium ion, hydroxyl ammonium ion, methyl ammonium ion, H2S gas, bicarbonate ion, and hypochlorous acid. And if you see their Kb values, they are very small, 1.8 times 10⁻⁻5, 1.7 times 10⁻⁹, 1.1 times 10⁻⁸. They are very in a different values, and if we have to compare two, suppose we have to find out which base is strong, which base is less strong, we have to compare the Kb values. So Kb value for 1.8 times 10⁻⁵ is more than the pyridine. So pyridine is weaker than the ammonia in the strength wise for the base. So this chart is used to explain the weak base. And one more thing I would like to tell you, that here for the weak base, when we try to calculate the pH of the weak base solution, we use ice chart again. Ice chart we make, right? So we'll see one example and then we can understand better. So let's see, one example is here that write the reaction and Kb expression for ammonia. So ammonia is a weak base, and ammonia formula is NH3. So once it will be write the Kb expression for ammonia. So Kb expression can be written only when we react it with the water, and water will be act as a solvent, and we know that this is a weak base, so we have to write this equilibrium expression sign. And what will happen, so this is a weak base, even then the nitrogen lone pair electron will accept one proton from water, so this will become NH4 and one positive ion, one positive charge, so this is become ammonium ion, and then water will left over as a hydroxyl ion. So this is the expression we have to write for ammonia for the reaction, and then Kb will be equal to ammonium ion NH4 and then OH minus divided by, we cannot include the water because this is a solvent, so NH3. So this is the example for Kb expression and how we can write the Kb. And the next, here we have one more example, that what is the molarity of an aqueous solution that have a pH of 11.17 and the Kb value is 1.8 times 10 to the power minus 5. So let's start to solve this question. We are talking about the ammonia, so we'll write NH3 plus water gives out ammonium ion plus OH minus. Right, we will write a chart, ice chart. Ammonium concentration, molarity of ammonia concentration we have to find out. So we do not know right now ammonia concentration. I will write like this one, and 0 means initial concentration, and since water is a liquid and it is a solution, so it will not take part, so I will just drag it. Product will be 0 concentration, and change will be here minus x and plus x and plus x. Right, so equilibrium concentration will be here ammonia minus x, and this will be x and x. So what will happen here, once we'll write the Kb expression for this reaction. Kb expression for this reaction will be product means x, ammonium ion, and hydroxyl ion divided by reactant, and this is E for equilibrium concentration. Equilibrium concentration will be NH3 0 means initial concentration minus x, right? So we know the Kb value, but we do not know the x value here. And also one more thing is here, that we know that Kb value is very small. So we can drop this change, so we can rewrite this expression. Kb will be equal to x square divided by ammonia NH3 0. That's it. So ammonia concentration will be equal to Kb multiplied by x square. So right now we do not know what is the x here, right? So what we can do to calculate the x, we can calculate, if we know the hydroxyl ion concentration, we can calculate the x, and hydroxyl ion calculation we can do from the pH. So since pH is equal to 11.17, and we know one formula, that pH plus POH is equal to 14. So we will use POH will be equal to 14 minus 11.17, and that will be equal to 2.83. So now we know POH, and if we know the POH, we can calculate the hydroxyl ion concentration also, and that would be equal to it would be 10 raised to the power minus POH, right? So POH we have already calculated, so it will be 10 raised to the power minus 2.83, and that will be equal to, once we will calculate this, it will come around 1.5 times 10 raised to the power minus 3 molarity. So now we know the x value or hydroxyl ion concentration, this much. So we can place this value into x expression, and then we can calculate easily that what will be the value of, or even we need not to here drop this x, we can include, because we are not going to, now it will be easy to do it like that. So we can do like that. So it will be slightly different answer, but it's okay. Ammonia concentration will be equal to Kb value is given 1.8 time 10 to minus 5, and then 1.5 time 10 raised power minus 3 raised power, and then we can calculate. So it will come somewhere near around 0.12 something molarity. So this is the one example how we can calculate the. You can double check this math also with your calculator. So let's see if it is correct. And in the next video we will discuss about the another example in the weak acid.